This is section 6.1. Today we want to talk about dot product in a new light, the length of a vector, and what it means for two vectors to be orthogonal. I'm going to have you read through this first page on your own. Since this is a video and I don't want to keep you here all day, I'm going to jump right to some of the definitions and computations on page 2. So the new definition of dot product is defined in terms of matrix multiplication. Instead of saying U dot V is this number, we're saying it's the matrix U transpose times the matrix V. So here I'm thinking of U transpose as a 1 by n matrix, and I'm thinking of V as an n by 1 matrix. And my answer, when I do that matrix multiplication, will be a 1 by 1 matrix, which we know is just a number. So nothing's going to change in terms of the way you dot two vectors. This is just a definition we're going to use to help us get where we're going. So for example, in this problem here, U dot V, all right, if you're doing this at home, you know, your homework, you're still going to say, okay, that's 18 plus 2, and then minus 15, which is 5. Okay, and let me just illustrate how you would dot with the new definition. U dot V is U transpose times V, which is U transpose is the matrix 3, -1, -5. And V, instead of thinking of it as a vector, we're thinking of it as a matrix 6, -2, 3. And when we do that matrix multiplication, of course, we just get 5. So pause the video for a second and try and find this vector W, which is defined as U dot V over V dot V times V. All right, let's see. U dot V, okay, I'm just going to do this in my head, multiply 2 by -1 to get -2, and then add it to 15. You get 13, and V dot V is -1 times -1 is 1, plus 5 times 5 is 25, so that's 26. So W is the vector 13 over 26 times the vector V, which is 1/2 of V, and V is -1, 5. And so that's the vector -1/2, 5/2. Okay, some properties of dot. These are the properties that we know to be true. Dot is commutative, associative. This is how scalars interact with dot. And D says that U dot U is going to be a non-negative number, so it's going to be greater than or equal to 0. And the reason for that is if you take a vector and dot it with itself, you're just getting the sum of squares, and so that couldn't possibly be a negative number. And here's some proofs that you can read through that use this new definition of dot. All right, so some important definitions. The length, or sometimes it's called the norm of a vector, is the square root of V dot V. All right, and sometimes it's nice to write that in a different way. Let me get to this definition first. A unit vector is a vector whose length is 1. So back to what I was saying before, this formula has a square root in it. Sometimes we want to square both sides and just write that formula as the length of V squared is V dot V. Sometimes it's more convenient to compute the length of V squared than it is the length of V, because then we can avoid the square root. And then if you want a unit vector in the direction of v, take v and divide by its length. And remember, the length of v is a scalar, so this is also the same as the 1 over the length of v times v. And if you took math, Calc 3 with me, then you're familiar with normalizing a vector, which means take a vector and divide by its length. So let's do that. First, let's just find the length of a vector. So find the length of v for this vector v. All right, so the length of v is the square root, by definition, of 6 squared plus negative 2 squared plus 3 squared, which is the square root of 36 plus 4 plus 9. That's square root of 49, which is 7. All right, so pause the video and you do the next one. Find the length of v for that vector v. And notice I've written v in linear format, and we're going to do that a lot in this chapter because otherwise our formulas will get very unwieldy. All right, so let's see what you got here. Hopefully you got 13 over 3. So the length of v, square root of 144 over 9, and then negative 5 squared is 25. 3 squared is 9. So that's root 169 over 9, which is 13 over 3. Let's use that to find a unit vector in the direction of that vector. So in this case, we want v over its length, which is 1 over the length of v times the vector v. Now, the length of v is a fraction. It's 13 over 3. So 1 over 13 over 3 is 3 over 13. Okay, so 1 over 13 over 3 is 3 over 13. And now multiply by v, 12 thirds, negative 5 thirds. And I get 12 over 13, comma, negative 5 over 13. And you can check that the length of this vector, let me call this vector w, the length of this vector is indeed 1. So it's supposed to be a unit vector, which means it has length 1, and so the length of w is 144 over 169 plus 25 over 169, which is the square root of 169 over 169, which is indeed 1. All right, so we're going to use that definition of length to define distance. So if u and v are two vectors in Rn, the distance between them is the length of the difference, u minus v. And so geometrically, if we think of those vectors u and v in R2, here's u and here's v, u minus v is the vector that goes from the tip of v to the tip of u. So u minus v is the distance between this point and that point. I'm sorry, I'm not sure what I just said. What I meant to say was the length of u minus v is the length of this vector, which we're defining as the distance between this point and this point. And we'll do an example in a minute. U and v are orthogonal if u dot v is 0. So this is a definition you definitely need to memorize. You also need to know this one. And then we have a Pythagorean theorem. And you might say, well, that's just the usual Pythagorean theorem. But what's different here is that this is true for any vectors in Rn, not just in R2. So R3, R4. And you don't need to memorize that. Okay, and I'll show you an example of that on the last page. Find the distance between these two vectors. So the distance is going to be the length of u minus v, which is the length. Let's subtract those two vectors. 4 minus negative 4 is 8, and 2 minus 3 is negative 1. All right, so that's the square root of 64 plus 1, which is the square root of 65. Let me just show you a picture of that, the geometry. U is this vector, 1, 2, 3, 4, 1, 2. There's U. V is negative 4, 3. This would be V. Now, the distance between U and V should be the length of this dotted line. But notice when we take U minus V, we get 8, negative 1. Let's plot that. That's going to be way over here. 2, 3, 4. This is the vector U minus V. Okay, now how is that related to that dotted line? Well, that dotted line is just this vector that's been translated up. So when you take U minus V, you get a vector what we call in standard position, which means its base is at the origin. But it really is, the length of this vector is the distance from the tip of V to the tip of U. All right, so now you try one. Find the distance between these two vectors, U and V. Pause the video, and then come back. All right, so hopefully you got root 50. So the distance is the length of U minus V, which is the length of negative 1 minus 4 is negative 5. 2 minus negative 3 is positive 5. And so that's the square root of 25 plus 25, because the negative gets squared out, which is root 50. So that's fine, leave it like that, or if you want to clean it up, 50 is 2 times 25, so this would be 5 root 2. Okay. Using the definition, show that U and V are not orthogonal. So we just need to show that U dot V is not 0, because if they were orthogonal, U dot V would be 0. So U dot V, again, we're just dotting like we would have, before this lecture started. 4 times negative 3 is negative 12. And then we add on negative 2 times 3, which is negative 6. And then we add on 0, negative 18, which indeed is not 0. You can also show that U and V are not orthogonal using the Pythagorean theorem. And so in this case, the same two vectors, I'll let you read this on your own, but I'll just briefly describe what I'm doing. I'm showing that the length of U plus V squared is not equal to the length of U squared plus the length of V squared. And so you can go through and read that on your own. And then I'm going to end the video and pick up with the next half of these lecture notes. But this box right here is from section 4.6, and it's a review of how to find a basis for row A, col A, and null A, and we'll use that in the next video. I just want to remind you, for col A and row A, for a basis for col A, if B is row equivalent to A, you're going to use the columns of A that correspond to the pivot columns of B. So you don't actually use columns from B, you use columns from A. And then for row A, you use the non-zero rows of B. All right, and we'll pick up next time.